going to talk about adversarial imitation learning and imitation learning for vision-based manipulations. All right, and we're going to see pretty state-of-the-art system. I don't know if you attended the talk yesterday at 4:30 from Sid Srinivasa, who used to be here, faculty CMU, and right now who leads some part of robotics in Amazon, Bulgarian controls. Thousands of robots that take part on this, package selection, packaging, routing, transfer, reading of barcodes, and delegating the package to the right place. I thought it was a very, very exciting talk. So we'll talk today about pick and place, much like what Sid did yesterday. Now, let me start by saying that we posted a survey last night in Piazza. We hope that you will fill in the survey. We may even give you 1 point for filling in the survey. It's very important you do that. 2 points. 2 points you'll get for filling in the survey because it's important to give feedback. All right, so we all keep improving, and then we'll have the fall break to really understand your feedback, see how we can adapt and so on. Okay, also that's good news. Fall break is next week. This is nice and exciting. And on Friday, for the recitation time, we'll discuss quiz 1 solutions. So please come in person for this. I think we'll still have a video. I'm still debating about posting that video online. I really hope you come in person to discuss the solutions here with the TAs. We may post the video online. We really hope that you don't keep notes down and distribute it to other students in other semesters. We really don't want this to happen, okay? Because there are, that many questions we can add each time. Yes. What? The slides are up. Can you check? There are 2 PDFs for today. The first PDF is about adversarial imitation learning, continuing what we started yesterday. And the second is about imitation learning for vision-based robotic manipulation. Okay? All right. Let's start immediately from where we left on Monday. Okay, we said behavioral cloning does maximum likelihood. We maximize the likelihood of expert actions, and for continuous actions, this ends up just being least squares. That's what we just said. And then we pointed out that unfortunately, this doesn't solve the problem of distribution mismatch between train and test time. At training time, the states are sampled from the expert. At test time, the states are sampled from the deployed policy. And unfortunately, these state distributions do not match. And as a result, there's no guarantees of the error of our policy. Last lecture on Monday, we said the solution to this are augmentations, okay? And we said that today we'll find a better solution to this distribution mismatch problem. Are we all so far okay? Do we have questions so far to motivate the problem? Okay, so here is the problem. The distribution of the observations that our network saw training time, okay, pi star, what the expert gave us are not the same set of observations that our policy sees as a test time, a deployment time. That's the problem. The state and action distribution matching objective. Okay. So how can we do this? How can we solve this problem? Well, it's just a distribution matching problem. And, nowadays, and since few years now, we do distribution matching with adversarial networks, all right? What does this mean? I mean, here is a taxonomy of generative models. Basically, what it means is the following. There is some data distribution, and you want to train a network, here our policy, so that the distribution of the items that you sample from your target network matches the data distribution. That's what it is. Now, in the case of images, then those the model that you're training, which you call the generator, essentially take random vectors and maps them deterministically to images. So the sampling happens at the input of the network, and then deterministically to an image sample, to the corresponding image sample. And you want this distribution of image samples to match the distribution of real images, okay? Now, just to give you already the analogy with our policy learning paradigm, what we'll go describe here in few slides, our generator will be a policy
the policy will just be generating actions conditional on states. It will not be generating states. States will be acquired simply by deploying our policy in the environment. Okay, so essentially we'll have our generator, our policy, spitting out actions. We'll deploy these actions in the environment. We'll see a next state. Again, we'll ask our policy, generate an action, see the next state, and so on. So we'll get our state action trajectories deployed from our policy, and we take those pairs of state and actions and feed them to the discriminator network. And the discriminator network will tell us, yeah, it seems that they match with the expert, or it tells us, no, they don't seem to match. And actually, more accurately, it's going to tell you, oh, if you change the parameters of your policy in that direction, I think you'll make this distribution much better. Does this make sense? This is what we're looking for. What we're looking for in the discriminator is learning signal. Which way should we be updating our parameters to make the distributions match? In policy gradients, what we did is we were looking for signal of how we're going to change our parameters to maximize the external rewards. Here, we don't have external rewards. We don't learn by reward. We learn by matching states and actions to expert state and action trajectories. Okay, very simple. Okay, so what we said last time, and I want to just quickly go through it again, is that GANs have these two networks that are jointly trained. One network is called the generator, and we use G to denote that network, that, as we said, takes random vectors as input. Okay, so we sample from a fixed Gaussian distribution, every element of that vector. Then we feed it through a network that has some parameters, and then we spit out an image. And the discriminator, we said, is just the image classifier, correct? That takes as input images and spits out yes and no. All right, there is a sigmoid as the last layer that essentially tells you how probable is that the image that you feed it comes from the real data. And it's trained supervised. That's it. Okay. Questions so far? So basically, we have some x's that are sampled from p-data. This is the distribution of real images. And dx is exactly the discriminator. And the discriminator is trying to say 1 for those real images that come from p-data. And at the same time, we have random vector z sampled from some constant distribution. And this distribution of this essentially induces a distribution over the image manifold. Okay, so every sample from the z corresponds to an image sample. Now, these images to you are not going to make any sense. They're going to be noisy images and so on, but we mean, you know, on the width by height by 3, this type of items, it induces a distribution over this type of items. And our goal is to have the discriminator to say 0 to those generated images. That's what the max across D will do. But at the same time, G is trying to minimize that. So it's trying to confuse the discriminator. Does this make sense? So G and D compete to optimize that objective. Is that clear that if we do the max across D of that formula, essentially D is incentivized to assign 1 to X sample from B data and 0 to X sample from the generator? Okay, that's how this, because then the D of the G of Z is going to go to 0. This is a 1, log is a monotonic function. Is that clear? Okay. Now, if we try to minimize G, then to do this, for this to be minimized, and G enters only in the second term, as you can see here, G is incentivized to make D spit out 1 for those sampled images. Is that clear so far? Okay. Now, how can we train that with gradient descent? Because this is what we know how to do. How we're going to train that with gradient descent? I mean, it looks reasonable. Everything looks nice and differentiable here. Do you agree? It seems that we're going to have some batches, right? In some of those batches, we're going to have real images because we need those real images from the first part, from the first term, and the other part of the batch will have generated images, which we need for the second term. Okay. And here is how it looks like. So we have our discriminator D and our generator G. Here's a real image, or a generated image. This is what you're going to be feeding to your discriminator, either real images or generated images with their corresponding labels. You're not going to confuse the labels. Every image has a corresponding label. The real image will have the label 1, and the generated image will have the label 0. And that's how you're going to be training the D, okay? So you'll update the discriminator using backpropagation on the standard classification objective. Nothing new here, all right? Well, I mean, this is new. The fact that the images are not now constant images, they're generated, but this doesn't affect the training of the discriminator. As you see, the red part is the only thing that changes here. We don't touch at all this G here, all right? Okay, and now here is how we're going to update the weights of the generator that sit on these 2 boxes, let's say. Schematically, we made 2 boxes to denote the layers of the generator, okay? Basically, we sample Z here from the constant Gaussian distribution, 0 mean unit variance. For each of those, let's say 50 elements of the random vector, we pass it through our layers, we get an image, we fit it to the discriminator, we flip the sign of the derivative, okay? And we backpropagate. And during this backpropagation, when we update the G, the gradient, the weights of the discriminator are not at all updated. The weights of the discriminator are only updated when you train it supervised for this, okay? So basically, we train a little bit our discriminator, and then we feed generated images, and we see which of those images fools the discriminator the best, okay? That's what it says. And that's how we pass learning signal to the generator weights. That's it. Now, I want to ask you the following question. Imagine that I initialize my weights for the discriminator and the generator randomly, and I get lots of real images, and then lots of generated images, and then I train the discriminator till convergence, and then I use this discriminator, frozen discriminator, to push gradients to update the generator. Would that work? Yeah.
I think it will be. I think it will work, but you want to make sure the D is not too.
It's not too good, because if it's too good, then there's going to be no generated image for which the discriminator will be fooled in any way. Okay, because it's extremely easy task to see real images of anything and say yes, they're real, and random Gaussian noise, random noise that essentially will come out from the randomly initialized generator and say this is fake. This is extremely easy task to learn for an image classifier. Okay. Now, what we do, the whole point here is not, we don't just train the network or the first network and then train the other. We jointly train them, okay? Which means we do few gradient updates for the discriminator, and then few for the generator, and then few for the discriminator, and few for the generator, and we go on like that. Is that clear? All right. Okay, let me ask another question. Imagine that our generator, no matter what random vector would sample, will always spit out a beautiful photorealistic image, for example, from this amphitheater. Super, very photorealistic. So if you give it to a human, it's going to tell you, yes, this looks like a real image. Would that suffice for this procedure to converge? Would this allow the discriminator to be fooled? So our generator always spits out the same image. Yes?
I mean, then the discriminator could just figure out if I see that image, then it's from the generator. If I see anything else, then it's not. And so it's still probably do a very, very good job of classifying.
Exactly. So our goal is not to generate one photorealistic image. The goal is to generate a distribution of images that are indistinguishable in distribution to a distribution of the real images that are in my data, what we call data there, training set. Is that clear? If you always spit out the same 1 or 2 or 5 images, the discriminator will totally maximize its objective by figuring out which are those, the fake ones, and always say 0 for them. Okay. Now, if you're wondering how can I get for few, okay, these are 100 numbers, for 100 random generated scalars to an image, well, this is one architecture that was proposed in Radford 2015, DC GAN. This is the paper DC GAN. That paper, by the way, was rejected by all conferences and then showed up in archive. Then in archive, it got a lot of visibility, and then it was accepted. Because it doesn't propose any new theory and so on. It just gives you practical considerations of how to stabilize training of GANs, which was actually a huge problem back then, and so on. Yeah. And it says the details about how to use batch normalization and so on and so forth. But basically, the only thing I want to show you here is just, first of all, probably you take those random numbers, you reshape them, you make something that looks like a 2D tensor, which you push forward through the convolutional layers and so on. Okay, and so in this way, GANs are usually object-centric. GANs cannot generate, general scenes and so on. If you want general scenes, the best architecture would be you sample multiple of those vectors, not just one. You sample multiples of those vectors, and then you have transformer layers to essentially decode them into an image. And each of those essentially vectors takes care of some local statistics around the corresponding location of the image that is assigned to it and so on through attention. So the important thing is that we have mini batches from the training examples and from the generated samples of the generator, and we alternate, and everything is end-to-end differentiable, and we train with stochastic gradient descent. That's what it is. Our discriminator is differentiable, of course, just an image classifier, and our generator is also differentiable. So I asked you already this. Both of these questions I've already asked you, and both of them we have already replied. So let's see why this is a good cost function. What would be the equilibrium, let's say, of that min-max game that the discriminator and generator are playing? Okay, well, what if I think going through some math here is helpful for you to understand what happens. Now, the truth is that during optimization, there is zero guarantee that whatever we're going to write here actually is going to happen, but it gives you an idea of why actually, what will happen when this game, let's say, what would be, in theory, what is the optimal point for this discriminator and generator networks regarding those distributions? Okay, the P data and the PG, the distribution induced on the image manifold by the generator. So let's first look. So let me just say one thing. So if we look at the logarithm, the truth is that around 1, the slope is not very high, okay? So if you want wilder slope, which means more informative gradients, it's better to go close to the 0. And that's why instead of having 1 minus d, we can have log of d directly. Why this is important? The reason this is important is the following. It's very hard to get off the ground at the beginning when you generate random images and they all look a little crappy, not realistic. At some point, the discriminator even needs to be sensitive. And if it sees something that is actually more photorealistic than others, should say, yes, I think I like this better, okay? So we really care a lot what happens when we're around 0, okay? Does this make sense when our discriminator spits out a 0? Tiny little changes, we want to have large impact on gradients. So sometimes you may see instead of 1 minus d, you may have this alternative rewrite formula there. But we're not going to use this for our analysis. We're going to go back to our original formula. And first of all, we're going to write off the expectations. So we have 2 expectations. Okay, and actually the simplest thing to show them is in this way. So both of them are on those images, which means what? Width by height by 3. These are these tensors essentially. And we have the P data, which is the natural, the distribution of natural images. Essentially, for some of those images, there is a thin manifold which have non-zero probability, and a lot of random images there, like noisy images, will have 0 under P data. And then we have Px of G, which is what? Which is the probability that our generator assigns to images. And to be honest, with the framework that I just showed you, there's not an easy way to read off that P G of X. And that's why GANs are also called implicit models. Okay, so there are some generative models for which it's very easy to read that probability of the image or of the item you're generating. For example, autoregressive models, right? For images. You generate 1 pixel at a time. Every pixel has some probability of some Gaussian. You multiply all these Gaussians and you have the probability of an image. Okay. Now for GANs, it's easy to sample from. It's just a feed-forward pass, super fast. But it's not easy to read off that probability. But you don't need to worry about that. Imagine that it exists. We just want to know that indeed, at convergence, PG of X should be equals to P data. That's the idea here. Okay, that's what we're looking for to find. Is that clear? We just said that our generator assigns a probability to each of those images, PG of X. And as it trains and its weights are changing, that probability distribution changes. And we want to see that indeed it approaches P data. Are we cool so far? Okay. Okay, so then since we have these two integrals, we better combine them into one. Okay. And let's try to see first what would the optimal discriminator do. So let's forget about the generator that generates those red X's. Okay. And let's just look at the D, the discriminator. So the discriminator at value assigns values dx, okay, scalars dx to each image. And let's take derivative to see what the optimum, where the optimum would be attained. So let's take the quantity inside the integral and differentiate with respect to dx. Okay, so this is something very easy to numerically to compute. And you will see that if you rearrange the terms and so on, d star of x, so essentially the optimum is attained when the discriminator assigns to x p data divided by p data plus pg of x. Okay. Well, assume that this p data and pg exist. Does this make sense? Now let's see what this pg will be. Let's imagine that this d star is going to be the optimal discriminator. So now whenever we see dx, we will actually go back and substitute with p data of x divided by p data of x plus pg of x. X, don't forget that x is just a sample from the image manifold, and p data is the probability under the real images, natural images of that x. That x can be an awesome, beautiful photorealistic image or some completely noisy crap image, anything, okay, that is width by height by 3. And pg of x is that implicit probability that we don't have access to, but it exists, that our generator assigns to it. So let's see. So we go back to our formula and put in the place of d, the d star that we just found. And let's start to reorganize a little bit the terms. So it is always good, instead of having the expectation under z, you have expectation under x's, because now they're both expectations under x's, under images. Okay. Same as before, we did exactly the same thing before. D star now is p data divided by p data plus pg. And let's combine, I would say, these two expectations, or let's see, no, before we do that, we'll do a tiny little trick. We can add and subtract log 4. I'll show you why this is useful. Let's forget about the minus log 4 and take the plus log 4 and make it, okay. Why would you do that? Well, now I'm going to show you why. Because log 4 is essentially 2 log 2. Now, this log 2 can be combined with these other terms, okay? Do you see here? And what we care to show here is p data plus pg divided by 2. So essentially, from, you know, the rules of fractions, you can totally take these two below here. You know that when you have you can imagine p data divided by 1, and this divided by p data plus pg divided by 2. So you know that this is 2p data and the multiplication of the denominator of the first and the denominator of the bottom, right? Okay, so now in both cases, it showed this p data plus pg divided by 2. Sounds good. Do you recognize what this is? We have an expectation of x sample from p data, the log p data with this distribution. This is precise the KL between p data and this distribution, okay? And so let's see. So here it is. The first term is the KL of p data with p data plus pg divided by 2. And the second is the KL between pg of x, p data plus pg divided by 2. All right. And these two together is the definition of the Jensen-Shannon divergence between p data and pg. And this is a symmetric, distance between two distributions. And it's always bigger or equals to 0 because it's a distance between two distributions. The smaller value it can take is 0 when the two distributions are identical. Okay. All right. So let's see. What is the optimal value that our PG should take to actually optimize that expression? Well, we know, as we just said, that DGSD is actually always positive, which means that our quantity is always bigger or equal to minus log 4. So you will see that when PG of X equals P data, when our generator is able to generate samples, to transform rather samples from, the constant, multivariate Gaussian distribution that has 0 mean vector and identity covariance to the manifold of real images as represented by P data, you indeed get the lowest value in that expression. Do you see? So now you saw that if you go through, let's say, the math of that formula, indeed, the best thing is attained when our generator goes close to P data. Does this happen in practice? Not really. For example, GANs are very well known for what they call mode drops. They drop modes of the data distribution. So you give them a wide distribution, and they decide to correctly beautifully model one part of it, and just forget some part of the data distribution that they didn't have capacity to model. Does this make sense? Okay. All right. So actually, you can see it here. So what maximum likelihood is trying to do is you have a model and it's trying to assign mass to everywhere in your P data. That's why you see this poor Gaussian is doing its best to capture two different modes. And what it does, it goes in the middle. And that's why we know that regression, that essentially, which behind regression, behind the squares is the Gaussian assumption. Okay, as we saw in the continuous actions, actually it fails dramatically. You have two modes, either the car go left or going to go right. And essentially what regression is, spits out, go to the middle, and you crash. Now what GANs do, they capture well one of the two modes, all right? As opposed to in the middle where indeed it is horrible and there is 0 probability just from P data. And, when you use GANs to generate images, while, Gaussian assumptions cause blur, right? They mix everything and you see something that doesn't look photorealistic. Actually, GANs are able to, launch specific modes of the image distribution and show some more photorealistic results. But we don't need to worry about that. We need to worry how we can adapt GANs to our policy to imitation learning. In this case, the generator will not go from random noise to images, will go actually will be this, our policy. We'll have conditional information, the state, and some random vector, and we'll spit out actions, okay? All right, and our goal would be, we want to find a policy that makes it impossible for the discriminator network to distinguish not between images, but rather between pairs of state and actions. So it's not going to be concatenated trajectories. We're not going to be feeding state action. Oh, here is a trajectory of 500 frames. Does it look similar to the expert trajectory? No, instead, we're going to be chopping those guys. Much like what we did in behavioral cloning. We look at individual time steps, but we're going to be feeding all of those to the discriminator. If you don't do that, and if you concatenate, then you need insane amount of data to actually look at these distributions, okay? So basically, in aggregate, across time steps, do state and actions from the experts look similar to state and actions from the policy that you're training? This is what our discriminator will tell us. Okay, so this is the second term that our policy is optimizing. If you remember, the 1 minus log became the log now. We have changed it. And this is what the discriminator is trying to optimize. That has two terms. In the first one, if you remember, there's no generator, right? So this is just a classifier. And the input to our discriminator right now, as we said, is not images, is state action pairs. Is that clear? Okay. So one way to think about it is the following. There is this discriminator network that you need to be constantly training, and then you're trying to optimize your policy to essentially maximize rewards. And the rewards is what? How much you managed to confuse your discriminator, all right? And what precisely is that quantity? You feed your discriminator your S comma alpha from your trajectories that you got by deploying your policy, and you saw the D of that S comma alpha. The higher the D, the more confused is the discriminator, right? Because you remember for real state and actions, D maps them to 1. Is that clear? Okay, so the output of our discriminator is essentially the reward we're trying to maximize with our policy. Now, the only thing we need to remember is that although extrinsic rewards, what we saw in policy gradients, are constant over time, they don't change. It's not like, oh, if you kill the monster early on during training, you get plus 100. If you kill it later, when you're more advanced as a policy, you get 30. No, it's always the same. Here, the discriminator rewards change because the discriminator is also being trained. Is that clear? Okay. So the reward for the policy optimization is how well I confuse the discriminator, which means how well I match the discriminator's trajectory, the demonstrator's trajectory distribution. Here is the reward. The log of this D phi. Okay. Yes?
Is there a difference between discriminating based on state action pairs versus the trajectory?
Yeah, so what you're saying is you decided to make your input to the discriminator a state and action pair, and why didn't you make it 5 states and action pairs, like a subsegment, correct? Right. Yeah, well, the problem is you may get a tremendous overfitting in that case. Right. You see the problem? For example, I want to tell you, even for images, you know what we do with the discriminator? Instead of feeding the whole image, not to memorize, we feed local patches of images. And say, oh, I want to make sure every local patch looks, let's say, photorealistic, exactly so that we do not overfit. So we carve chunks of images and fit it. Does this make so? Basically, as if you have a discriminator that instead of taking an image, it spits out 1 yes and no, it spits multiple yes and no's. It's yes and no's for every patch in your image. Right. So it's the same as here. It's as if you have a long trajectory, you grab patches and you ask your discriminator for every patch. Now, if your trajectories go towards crash, okay, clearly I'll see that, you know, they're different than the states and actions of my expert that do not crash. Okay. Yes?
So does it mean, like, if we feed the trajectory to the discriminator, it will be less challenging? So that
yeah, it will be less challenging. It would be much harder to confuse it and to get off the ground. Yes, I think so. Mm-hmm. Yes. Yes.
Is it expected that this will do better than training the generator using just supervised classification?
Very good question. We'll go now to the comparison. Now, the good thing, so let me show you the algorithm and then we'll go exactly to this comparison between behavior cloning and GAIL, generative adversarial limitation learning. Okay, so just to be clear about the pseudocode, we have a bunch of expert trajectories and we have some initial policy parameters and initial discriminator weights. Of course, we initialize them randomly most of the time, okay? And then I sample some agent trajectories, okay, sure. And then I update my discriminator and my policy. My discriminator is updated through this objective that we've seen before, okay? And now the question is how my policy will be updated, guys. That's my question for you. So the discriminator is just a classifier that takes you from state actions to, is this from the expert or is this from your policy? How we're going to update our policy is the question. Who would like to say something? We know the rewards. The rewards are log d f of s comma alpha, okay? So for every state and action in your trajectory, you have an idea of how good they are, how well they have, confused the discriminator. So the most, yes, does anybody want to say something or? Yes. Yeah, there is no Rmax here. We have continuous actions, let's say. I mean, you can also have discrete actions, but well, why don't you remember what we did in policy gradients, right? In policy gradients, you would have a policy deployed in the environment, get batch on trajectories. For every action, you would estimate an advantage, if you remember, by computing instantaneous rewards plus gamma v of the next state minus the v of the current state. If you remember, that's the definition of the advantage. So now you have an idea of how good the state and action is. So why don't we use policy gradients exactly the same way? Grad theta log p theta, log d of that discriminator s comma alpha, which means what? The actions that are lead to discriminators, confusion will become more probable, and the actions that are lead to discriminators not confused will be less probable. Okay, that's precisely what this gradient does, right? Do you agree? Much like exactly what we said with the alphas, right? When the alpha was positive, this gradient makes you to increase the advantage, the probability of that action has high advantage, and to decrease the probability of the action has negative advantage. Correct? Okay, and that's pretty much it. That's how it works. Now this is very confusing. Why? Because it's an imitation learning method. Okay, it is learned from expert trajectories, no external reward. But at the same time, for this to run, you need to have an agent that you deploy the policy in the environment. You deploy the policy. You don't just sit there and then train a classifier of like we did with behavioral cloning, right? And you deploy it, so you see the mistakes of your policy. The discriminator sees that distributions don't match and updates the generator to help them match better. And somehow now magically you don't need to do your crazy data augmentations that you had to do for behavioral cloning. Okay, that's the idea. Now, one question I have for you is, can I learn under this framework? Can I learn from both external rewards and imitation signal? Let's say I want to play Atari, and I still know the rewards of the Atari simulator. I have the environment spitting out rewards for me, and I also have some expert trajectories. Why not? And of course, we can discuss the pros and cons of this. So why would you care to do that? And if it's easy or not under this framework? Yes.
I think you can. You can just make your loss function multi-part. You have a part that's your acquisition learning, and then you can have a part that's your reward. And then you could scale them however much you care.
You can weight them, you mean?
Yeah,
yes.
You can weight them however much you care. And then maybe you'd want to do it if your expert's pretty good but not a genius. So you want to still have some possibility of finding some novel solutions.
Excellent. Yes. So your colleague is saying the following: why would I care to do that? Because first I want to get off the ground fast. While if I do RL all the way, it's going to take me forever. So I really want, when I'm in the beginning, I have no clue what to do. I want to imitate the expert, but later I want to do better than the expert. Will Guile ever do better than the expert? The way we just presented? No. It's going to stop when the state action distributions match. Or it doesn't even have a clue of external rewards. Now, if you have external reward and you at the same time you try to maximize that external reward, then you can do better than your expert. And also your colleague talked about weighting between the two terms. So by the way, just to be concrete, inside the log, along with your D, which is the R of the Guile, the reward of the Guile, you can have this other R. You just add them together. You also put some alpha to weight them. And what does it make sense, guys? Which term would you weight more? Which term? Let's say you have a weight for the external reward and a weight for the imitation, which is the discriminator. Which one you would decrease over time and which one you would increase? I mean, one will be the alpha and the other one minus alpha. So this, yes, which one would you?
Decrease the imitation over time.
You would decrease the imitation over time because you say, towards the end, I don't want to be imitating. I want to actually be maximizing the external reward, right? Because I cannot do both at the same time, right? Excellent. Yes, that's good. So now we're going to see a method that does that. And let's go. So we're about to see a method that does exactly this. But let's go back to the question of your colleague that said, is this better than behavioral cloning? And the answer is, yes, behavioral cloning reduces imitation learning to just supervised learning. That's true. Guile instead is a reinforcement learning where the reward comes from imitating the expert. Guile requires way more interactions with the environment, okay? Behavioral cloning potentially and the Dagger extensions that we discussed for the augmentation requires much less interactions with the environment, which is, we care a lot about minimizing those. And the last question is, you've already answered it, guys, that neither BC, neither Guile can outperform the expert. Yes, please.
Would you say that Guile is more sample efficient with respect to expert trajectories then?
No, Guile is very sample inefficient. It requires a lot of deploying the policy in the environment. Now,
Deploying the policy, but say it's very expensive to get an
oh, exactly. So very excellent point. So your colleague says, yeah, sure, it is more sample efficient because you need to deploy your policy in the environment, but you don't need to iteratively query the expert, which we know that for many cases you cannot do, right? You cannot, we said how difficult it is to go back to the humans and ask them, oh, how can I recover? And so on. Of course, this assumes that you should be able to deploy those unsafe policies in the environment. That usually means only for what? Simulation environment, this holds, etc. Okay. Now, by the way, let me just say something very obvious. You can totally combine the two, and people do that all the time. You start with behavior cloning. Instead of starting your policy randomly, you start the policy with behavior cloning, and then you do the Guile process just to get the distributions to match. Okay. So we'll show that in a second. Yes.
So you mentioned like with the policy gradient, how to use the advantage computed over around you. Would there be any advantage to using the discriminator value over that horizon as well, or is that getting to the full thing? How to decay, or like just looking at the next step?
I see. Yeah, I see what you mean. So I think what you're trying to say is, when we talked about policy gradients, right? Every action would be assigned the sum of rewards from that time onwards on the trajectory. You remember when we said we'll exploit the temporal structure? And now your question is, I have the trajectories organized into state action sequences. Will I only look at how well I confuse the discriminator now, or also how well I confuse in the future of the trajectory and sum those rewards, right? I think you can totally do that, exactly what you just said. Yes, you can. You should sum them up and see and do look ahead. And this has nothing to do with the discriminator. The discriminator can still run individually on each one of those time steps, but you can, because you know how states are arranged into trajectories, you can sum them up for you to take gradients. Exactly what you did with summing the rewards and to compute returns, right? Yeah.
But you're reducing the sample efficiency, right?
I mean, it's good to do, meaning that you are about to, let me see. So, for example, you're about to crash, and further down in the trajectory you crashed, and clearly when you crash, the state action pair has extremely low value of confusing the discriminator. But early on, you kind of confuse him. You haven't deviated much. By looking ahead and summing those values, then you propagate it as if you do look ahead and you propagate the bad thing that happened to the current action, let's say, or something. Does this make sense? Yeah, I don't think people do it when they use it, though. Actually, I'm not sure. This is a good implementation. I need to check. This is a good question. Okay. This is a good question. By the way, we had Guile as one homework, but it was horrible. It was terrible. We only had it in one semester. Nobody got to work. It was also back in 2017. People didn't know how to train guns yet very well. And in fact, we got comments like Guile doesn't work as a comment about the class. Guile, but which is true. I mean, but it's such a beautiful. I think it's pretty beautiful theory. So now I'll show you a couple of other papers that actually have it there. Okay, yeah. So do we want to say something else? I have one more interesting thing to say. Imagine that you have an imitator that has 5 fingers, and imagine that you have a robot that has a 2 gripper, okay? Which means the actions don't match between the imitator and the student, the executor. You can still use Guile to do that. And this is very interesting now, because indeed you need trial and error. You don't have the actions. Behavior cloning is not an option anymore here. Okay, behavior cloning is not an option. And basically what you're trying to find is, how do I need to move my end effectors so that I can get the same state distribution as the expert? Okay, and I think this makes tons of sense. Basically, the only thing I'm showing here is this becomes a very similar, reinforcement learning problem, where the input to the discriminator is just the state, okay? And it's your job through exploration and sampling of your actions to actually get off the ground and indeed get to some state that actually matched the state of the teacher. Okay, like just to give you a concrete example, your goal is, the teacher, the expert pushed the bag from left to right. You don't have a clue how to push the bag. So you start like that randomly. The bag is stuck. The discriminator says this is very bad, very bad. At some point, you got lucky and you do like this. Okay. And the discriminator says, okay, great. I'm more confused now. And they're like, oh, great, great. And then you start pushing and then you confuse more. And then do you see how you get off the ground? Now, if you don't manage to move it at all, there is zero. This is called the cold start part, that nothing is updated, basically. Okay, that's the problem. But in any case, I think this is very, very interesting for you to know. Yes.
So with generative adversarial-based models, are they more likely to get stuck in near optimal states that the teachers know, instead of finding like global optimums that might be hard for the teacher to perform?
Very good question. So does anybody want to answer? So basically the question is the following. Does guile get stuck into imitating the expert versus optimizing the reward of the environment and performing which potentially would measure how optimal you perform a task? Is this what you're asking?
So if an expert tends to do like a safe but high reward strategy versus a dangerous but extremely high reward strategy, would it tend to go towards the distribution of safe strategy?
One more time, say it one more time.
Yeah, so like for the example of the pole vault, if the experts all do the normal pole vault strategy, would it ever learn to do the turn your back pole vault strategy?
Oh, we're talking about the back flip.
Yeah.
So you're saying, would ever guy learn to do something more intelligent than the expert?
Right.
Yes.
It doesn't even know about the rewards. Like its entire reward is just imitating. So it's never going to do something that like maximizes the other rewards more because it doesn't even know about them. All it knows is it gets reward for imitating what the experts do. So in that case, it'll just get reward for like doing the same type of jump that the other guys do. Because it doesn't even know about like the other rewards. So it wouldn't be able to learn anything else.
Well, I mean, where you initially train via Gale and then you switch.
Oh, well then, yeah, in that case, because like at that point, like once you like switch, like you at least know how to jump, right? So then from there, maybe you can learn like some other thing, right? Or like maybe you like grippy it like this way first, but then like now that you know how to grippy a little bit, like grip it from the side. Like, now that you're smarter.
Great question. So I think so now I understand your question. So your question of your colleague is, once you shape the policy by trying to do something that the expert does, how easy is for the RL method to actually discover a much better strategy versus not initializing the policy whatsoever? Okay, is this what you're saying? Yeah, great. So the truth is that in general, RL would usually explore nearby the initialization. Now I can guarantee that if you randomly initialize, if you give it enough compute, it will get off that local minima. It's not clear that a random policy would do better and you would so much accelerate the exploration and so on, unless you have a really good exploration algorithm. If you have such a good exploration algorithm, you may as well add it in your BC-shaped, behavioral clone-shaped pre-trained policy. Okay, great. Okay, so this is something that I mentioned last time, which is super simple. The reason I mentioned it with the goal conditioning is because I wanted to talk to you about goal condition behavior cloning, which is when you're trained from expert trajectories, it doesn't need to be that all trajectories have the same goal. You can add that goal annotation in the trajectories. And we also discussed about goal relabeling as an augmentation approach, which means what? You go from a tuple of state goal action 0 as prime to a stale goal under this alternative goal G prime. A failed execution now became a positive execution. And there was a question on Piazza, how goal relabeling helps? Well, it gives you, for other goals that you're pursuing G prime that are all in the states of your goals, it gives you positive samples. You don't need now to again move your hand randomly to get there. You have it already from before, right? So basically, alternative goal configuration can share training samples. Many of them will be failed across all the Gs, and some of them, for some G, that specific configuration will be successful and will have a reward of 1. That's all. It's very simple. So here's maybe one question for you guys that is difficult. In which of the tasks you think that goal relabeling as a data augmentation will help the most? Picking an object up, reaching, pushing an object to a location, or all of the above considered jointly.
Reaching would be my best guess.
So there's going to help a lot, because no matter what you do, somewhere going to reach.
We'll reach somewhere.
Great. Yeah, I totally agree with you. Next, which one is the next easier to that goal relabeling is going to help? Push. Okay, so what's wrong with picking? Yes?
It requires a complex set of actions to get to the picking up place. You got to move your hand there, then close your hand, then pick it up.
True.
So whenever you relabel it, if you never actually lift it off the ground, all of your new goal primes are going to be on the ground goals.
Yeah,
You
right.
want to learn how to do that one.
Right. So your goal, your colleague says each time you fail will never be successful for a picking. You just didn't even touch the object, or you touched it and actually you barely moved it. Excellent. Yeah. Unfortunately, yeah, that's the reality. But there is this paper, and the reason that this paper is included into our readings is because they have a lot of interesting ideas. First of all, they have guile. Then they make it goal conditioned, which is trivial, and we're going to show now the extension. Next, they combine RL and imitation rewards, which is some very reasonable thing to do that we'll see very often from now on. And they use goal relabeling as an augmentation. And to be honest, many papers we'll see, guys, are going to be this type of thing, like mix match on multiple ideas that we've seen in different papers in isolation pulled together. Okay, and now you'll see what I mean. Here is how goal guile looks like. The only new thing that I see here is that extra G conditioning on the discriminator and in the policy as well. Yeah, the policy as well has the G. I don't see how the policy is there now. Yeah, so maybe, so for sure the G enters into the policy, otherwise the policy doesn't know what is the goal. This is precisely what your colleague said earlier. He said, I will just have two rewards. One is the reward of the guile, which is the log of the D of the discriminator. The other will be the external reward, our task, and I'm going to weight them. That's precisely what he said. And also, I just want to make sure to tell you that our task, as we said, is constant. Beginning of the training, end of the training is the same, while our guile changes as the discriminator is being updated. Okay? And so in that particular paper, they use the DPG. What does the DPG do? Well, it trains a Q network, if you remember. So you need to have some other set of weights, W or phi. If you use phi for the Q, you cannot use phi for the discriminator, right? These are completely separate networks. And essentially, it updates the policy by backpropagating through the Q, if you remember. So we have continuous actions here clearly. And then it also does goal relabeling, which means what? If it has a state action next state goal in the demonstration trajectory, then we will add the same tuple, state action next state, but for another trajectory. For another alternative goal configuration, G prime, usually as you pointed out last time, the goal state and the state space coincide. Basically, I consider a goal everything in my state space. I want to be able to reach at every configuration in my state space. And here, indeed, the G is, the alternative G prime is actually the state that my tuple reached. That's all. So they do this data augmentation. And you can use this relabeling in all your methods. And here, essentially, GC means goal condition BC. This is behavior cloning. Goal condition BC plus hair, hit signed experience replay, and goal guile, where you use also the adversarial reward. Okay, and you see that how the BC with goal relabeling essentially is able to visit much more of the state space much faster. What have I want to say here? Nothing. That's pretty much it. Here is a pseudocode. The pseudocode of that paper is kind of simple, right? So we sample a goal G, which is, so this is the most, let's say, sneaky part of the papers, that somehow they assume that this goal state is null. Do you see? And you can sample from it and so on. This means that your state is either very simple, some maze where you move and you know your X, Y, etc., or you know where the objects are in the environment and your gripper and so on, and your goal would be, oh, I want my gripper to be in this particular location or in this particular location, and I train my policy here, and once the obstacles change, oh, I really need to retrain from the beginning because actually the other obstacles don't show up in that state space in the first place. The state does not encode anything about the obstacles. So essentially, they have this built-in assumption that I trained for this particular environment where the backpack is right here of how to reach, let's say, to the zipper. And once the backpack moves, then I need to train from the beginning because this backpack actually doesn't even show on my state space. Do you see? It's actually, where does the backpack show? On the weights of the policy network. The policy network has learned not to go there because it's going to hit the backpack. It doesn't. So naturally, you design your method so that it will not generalize to other environments, but you don't need to worry because the second part of the lecture is all about generalization. So different papers worry more about discovering interesting solutions and behaviors in a given environment, and other papers worry more about transferring solutions across environments. Okay, so clearly imitation learning is not worried at all about discovery. It says, I have an expert. The expert is going to tell me what to do. I worry more about generalization. I don't want the expert to show me what to do in every little, variation of the environment. If it shows me how to open the zipper here, if the backpack changes, I don't want someone to show it to me again. If there is a new backpack, similar though, I still don't want for me to need the new demonstration. Okay, so my ability to generalize the shown behaviors is actually critical. So this is the second part of our lecture. Okay, so with sample goals, we talked about this problem. Then, yes, so we have an expert buffer and the replay buffer, which is expert buffer is the expert demonstrations, replay buffer is the experience of the agent itself. Then we relabel both the agent transitions and the expert transitions by essentially adding some tuples under alternative goal configurations. That's what means relabeling. So I come up with different GIs, and usually those GIs are the resulting states, as you see here. GI is the ST plus K, where the K is sampled from some future of the trajectory. Because I know that this, if I go the state in the future, I'm going to reach that particular goal. Okay, that's it. And then annealed Gale goal essentially means that this delta changes over time. It happens exactly what your colleague says, that the delta of the imitation goes down, okay? And so then this 1 minus delta goes up, which is the external reward. Here is the Q, which we needed. It's just a least square problem to fit the Q. And then we update the policy by backpropagating through the Q network because we're using DDPG. We don't use policy gradients, that's all right? So the Gale that I showed you in the previous lecture, in the few slides ago, was using policy gradients. That's fine. Here, you consider you backpropagate through your Q network because you have, let's say, deterministic policy. Does this make sense? Okay. All right. And this ensures outperforming the expert. This is what you just said earlier, the fact that we need to decrease that weight of the imitation. And the result is the following, that goal relabeling helps, Guile helps, so basically they have nice ablations, that's all the different ideas actually are helpful, okay? And the reinforcement learning alone, actually, without any imitation is also pretty bad. Okay. So there is another paper that I have as a required reading and the reason that I have as a required reading is because it, again, has similar combinations of ideas. So basically combines imitation rewards and task rewards, okay, much like the previous paper. It has a very interesting state resetting, which is only possible in simulation and is one of the very basic ideas of how do you use demonstrations. So one way to use demonstration is you do imitation and you have an imitation reward. Another would be to pre-train your policy with behavior cloning. Another would be to wake up in a state from your teacher, okay? So if the teacher, let's say, picks up an object and you are in a case of kinesthetic imitation, so you have access to that state, then you can reset your simulator in that state, all right? This is extremely, extremely helpful. The other very famous idea is asymmetric actor critic, which is the following. You want to have a policy that operates from pixels, but you want at the same time to learn fast. So you use ground truth state information of where the objects are in the simulator as your representation of the state for your critic network, and you use images as input to your policy network. So they call this asymmetry, because the critic and the actor network are not symmetric. Okay, the actor is trained from images, the critic is trained from ground truth state. Why this is a good idea? Yes?
The critic can be like a really smart teacher that helps in updating the policy network.
Mhm.
And when there's better estimates of value that are used to update the policy network, you can learn that better faster.
Yes. And what happens at test time?
At test time, you've already learned better, so you do better.
Right. So is the critic used at this time or no?
If you're just rolling out, then you don't need it later.
You don't need the critic, you just deploy the policy. So you don't need the ground truth state information at test time. You only need that ground truth state information at training time. How can you obtain it? Well, you can put more cameras in your workspace. You can put in your objects these AR tags, and then have mockup system, and then you track the pose of the object based on that AR tag. I'm not sure if you know this type of techniques. And then at this time, you don't need it because your policy network operates already from images. Okay, that's the idea of that asymmetric actor critic. Okay. So the discriminator doesn't use images and uses this ground truth state the same as the critic does. Auxiliary task, let's not worry about it because we're going to have a whole lecture about auxiliary tasks and so on. And sim to real jump via domain randomization. Again, we're going to have a whole lecture about sim to real, how we close the gap, and about how important domain randomization is. But basically, the ideas that we need to worry about is this, which we saw also in the previous paper, is our discriminator that uses scene state, which means where the objects are. This is what you feed as a state representation for the discriminator. The asymmetric actor critic, which I don't think I'm going to, there is a paper exactly called the asymmetric actor critic. I don't think you need this as a required reading just to pick up this idea and to be able to answer such a question in a quiz. Just read that paper and it's pretty obvious. And state resetting, extremely important, extremely biologically implausible to wake up in stage states like that. But in any case, we do it in simulation. So let's see one by one. Combine imitation and task rewards. It's exactly the same thing that we saw earlier. Exactly the same setup. We have our guy, we have our task and so on. And we have the discriminator operating over states and actions, it seems here, because we have the actions. State resetting. We can reset the world however we like, and we have full state information to be able to, it's as if we are gods and we say, oh, now I want to wake up, opening the fridge and holding a sandwich in my hand, and this happens. This is what means state resetting, okay? This asymmetric actor critic, you did it actually very well. That state, just to be clear, is XYZ. It's 3D information of where the objects are. So this is what enters into critic. Yeah, so this is important to know. About this, as we said, we're going to have a whole lecture. So this is how things look like. Here is the discriminator. Psi is a very nice, letter of the Greek alphabet. You need that many letters because policy is different than the critic, which is different than the discriminator. These are all separate networks. Okay. So here is V phi, the value function, and P theta, which is the policy. Yeah. So the policy takes images as inputs. And here is the ground truth state. The centroids, what you see as dot is the 3D centroids of the objects. And somehow all the objects are going to be similarly shaped cubes because I'm not sure even if they pass the size of those objects in that state and so on. So whatever is not fit into the state essentially is hardwired on the weights of the network that is trained on top of that state. And again, if you see here, Guile alone cannot do it. But, reinforcement, Guile plus behavior cloning plus reinforcement learning actually does better if you read the whole paper, let's say. So that's it. Now we know about adversarial imitation learning, and we have 17 minutes for some super exciting vision-based manipulation. Talk Nippon. So here I think this is the one. I hope so. So before I jump into our new topic, do you have any questions? We just discussed about imitation learning for with behavioral cloning, very handy for autonomous vehicles, right? We always assume that the action is available. We talked a little bit what happens when the action is not available, okay? This is extremely important. No problem. You can actually do trial and error so that you can match the state trajectories of the expert. So why the concepts can be a bit confusing in today's lecture? Because we saw while I have some expert demonstrations, still I need to use reinforcement learning, either because the action is not available, I just have visual demonstration, all right? Or because I don't want to do these augmentations and I want to do distribution matching. Okay, that's why. So, but don't get confused. If you understand the motivation behind each, design choice, then it is totally okay. Does this make sense? Any questions? Okay, so today this is a combination of slides for transporter networks and goal condition transporter networks, which is a very recent and very, let's say, successful framework for pick and place. And it's a very time relevant to discuss about it because yesterday we had this nice talk from Amazon Robotics. And all the things that they do, these robots, are pick and place. And in fact, Sid said that they will have 10 million picks per day, which I think it's crazy, across all those robots that pick objects and put them in the buckets or put them into these moving corridors and so on to delegate them where they're supposed to delegate them. Okay, so here is transporter networks. So by the way, the first thing, this is the most important thing to remember. Reinforcement learning overall worries more about discovering behaviors, right, through trial and error, while the truth is that human brain is mostly worried about transferring those behaviors. The reason, because we learn a lot from imitation. We imitate our parents, we imitate one another. That's why they say the second kids are much intelligent. They pick up things faster because they have the brother or older sister there, and they just copy paste much faster from that sibling. Okay, so a lot of things we learn through imitation. Okay, a lot of things. It's very hard to say that we innovate that much. Okay, but we're very good at adapting behaviors. So imitation learning is really, really worried about such adaptation because once we, let's say, write a paper and we want to compare an imitation learning method with another, we'll compare this against two axes. Number one, for a given variation between train and test, how many, and accuracy, how many demonstrations you use versus how many I used, and for the same number of demonstrations, how different can the test environment be from the train environment? So these are the two axes of success. How much can the test environment change? Does it need to be the same backpack in different orientations or different translations? Can I rotate it completely? Can I turn it upside down? Can it be here a different backpack? Will you still be able to open the zipper and so on and so forth? And how many demonstrations can I learn for very, very few demonstrations? Is that clear? All right. Now, the first confusion comes from the fact that there are two famous transporter papers. They're both called transporter networks and they're extremely dissimilar, but they just picked the same name because it's just the field is very big. So that's it. But we'll talk about transporter networks from actually, I don't want to say Google because the other is also Google. It's from DeepMind. But in any case, the first one is from Google Brain and the other is from DeepMind. And they're completely different topics. But look at this beautiful robot doing all these nice things. Well, some of them are in simulator and some of them are in the real world, okay? And we'll discuss how with very few demonstrations, we can have robots do all those tasks. And what you see is we have a sanction gripper. There's no two fingers here. This also works with two fingers, but I think all of them are with sanction gripper. Okay. And it was interesting because Sid yesterday also talked the problem with the sanction gripper. You cannot manipulate a book with the sanction gripper. Actually, you'll destroy it. So that's why he said, sanction is great, but sometimes you need really a two-finger gripper so that you grab a book in the way that it doesn't open it and so on. Okay. Now here is my main point is as follows. I want to ask you, imagine, so the setup is going to be here the following. We're going to have an expert to tell us how to perform a task, okay? And imagine our task is, this is very simple. Let me show it to here. Our goal would be to pick up that red thing, the red L-shaped object, and put it into that L-shaped hole, all right, with a suction gripper. And what I will do as an expert is I'll just go and pick it up. So I will show you a point where to pick it up, and I'll show you a point where to place it, all right? And my question for you is, imagine you have a policy and you want to learn from some demonstrations, okay? Imagine you have different L-shaped objects with different L-shaped holes and so on. What would be that action representation? This is what we'll discuss. What should be the action representation so that under environment variations, which means what? The L-shaped object may move, the L-shaped objects may be oriented, okay? The background may change color. Still, our policy should be robust and should be able to achieve the task. This is the idea here. Okay, great. So would anybody want to say something about this, like to propose some baseline idea about how this policy network should look like? Yes, Maxwell wants to say something.
Maybe like the action should be in terms of like where the red block is and like where we're training it to be is. We like think about like orientations as if those are the origin like points. That way it's kind of robust to wherever the red point starts. As well as closer to eventually.
So okay, yes, I agree. So our input should be the image, I would say, correct? Yeah. So what would be the output then?
I guess the output is like how you get your button.
How your gripper should move,
yeah.
Like dx, dy, dz, for example. Great, excellent suggestion as a baseline. Anybody, any other ideas? So basically, we're going to have an image, and then what are we going to have? Let's say we're going to have some convolutions, and then we'll have some average pooling or something, and then we have that image, and this, in that image, you see which objects and which goal, right? And then you'll take the image and average pool or do some other combination, then you have a vector, and from that vector, you'll spit out dx, dy, dz of the gripper. Do people agree with this suggestion? Any other ideas? So this is precisely what will not work. This is precisely why this paper is so famous, because that's what people did before. And this is, the recipe for lack of generalization. Why this is the case? Because actually, there is an amazing slide later that exactly compares the transporter representation to what Max suggested, which, by the way, as a baseline makes a lot of sense. But I think the whole point of the set of slides is to explain why this is a bad idea. Okay, so I'll show you now what transporter does. First, it says I need to find the region of interest, which I need to pick. And, there's a dot there. And then I need to figure out where to move it. That's all. Now, I say, guys, the following. What if, let's say I give you as ground truth, I'm an expert, and I demonstrate where to pick the object. I just picked it myself. So it does make sense to have a network that takes an image and spits out at a heat map of where to pick the object. Okay. And we said earlier, we need to move the gripper there. We need to, the output of our policy network should not be which object to pick, but how actually to move the gripper. Well, it turns out you can use a planner to go there. You can just use a planner where you give it a location, okay? And your suction gripper should be like disoriented. And this planner, have an idea of the 3D occupied space and just solves the problem and goes and picks it up. Does this make sense? So the only thing you need to worry is where is that contact point? Do you see? And then you use a planner to go there. And we'll see why this is useful. But let's see. Let's assume we have a pick. We pick the object. And indeed, our policy network spit out the location of the object and has a heat map there. And it's just essentially a pixel classifier. Yes or no. This is a pixel to pick it up. This is not a pixel to pick it up. That's all. All right. There is no knowledge about objects here, by the way. It's just an image. And at every location of the image, you have is yes and no. Yes, I'm a good pick location for this, or no, I'm not. And whatever you see as white is yes, this is a good location. Now the question is how we're going to predict the displacement. So I want to displace it right there. What if we predicted dx dy, right? So we take the image And then we can also take into account the heat location and feed it into another network and spit out dx dy, correct? Now, let me tell you, to learn the transformation from the image into the displacement, it's extremely difficult for a network, okay? Now, there is, so basically this is, again, the recipe for disaster. So this is not what we're going to do. We want to have a representation that is retinotopic, that operates on the image space directly. So I want to predict the place location as the pixel on the image where I want to place it. And because now I care about what I picked, so here's the difference. So the baseline would be, I have the image, I have one network that spits out the pick location, and another network spits out the place location, correct? Just pixel classifiers, two separate pixel classifiers that I train from expert pick and place actions. Do you agree? This is very close to what's happening. There is one tiny little difference, which is the following. Because you may have orientation, you may need to rotate the object that you picked. This thing that we just described will not work. Do you see why? Because if the L-shaped is oriented differently, then you also need to account for that rotation. Is that clear? Okay, so then what we're going to do is, instead of having a placing network, we're going to have a peak conditioned placing network, which is the following, very simple. You will compute the features in the image, so every pixel has a feature vector. You will crop a feature, you'll crop whatever is inside the box, and then you will do a convolution, okay? And you're going to do a convolution of that everywhere, and also you're going to rotate it 30 different times. You're going to change every little orientation and do 30 different convolutions. And then you will take the argmax across those rotations and locations in the image. And that will be, the output. And the output would be not only where you're going to place, but also what orientation you need to do, how much you need to rotate to place accurately. Is that clear? So this is the most important slide to understand, because, and it's totally cool to repeat it, because, this is kind of very important. Yes?
I think it's better. So the target location is something that looks like the shape of the object, but not necessarily that object itself.
Very nice. Great. So what you're saying is, but what needs to be, the place location can totally be, take a strawberry and put it in a yellow plate. And the yellow plate doesn't have the shape of the strawberry. Okay, but I gave you demonstrations that I pick strawberries and put them in the yellow plate. So the only thing you're going to do is you're going to take the strawberry, crop it, do some cross convolution, and somehow the strawberry will be placed in the yellow plate. Now, in this particular case, you wouldn't need to do peak condition placed, right? You can just have a placing network because you don't need to rotate the strawberry or whatever. But it doesn't matter. Well, it's okay. We're just going to have this general architecture that wherever we pick, we crop some features, we rotate 30 times. For each rotated version of the figure patch, we do convolutions, and then we train so that after the convolution, the argmax is exactly on the ground truth place location. Does this make sense? Okay. And then you let the network figure it out. Some placing locations, let's go back to the tasks. I liked your question. So for example, in this task with the letters, then indeed, where you're going to place it has to do a lot with what you're picking up. So the M-shaped hole will be very similar to the M shape. And in some other cases, for example, in the plates, it really doesn't have anything to do with the shape of what you picked up. But it doesn't matter. The same network we're going to use, but unfortunately, we train it in each task separately. So whatever you see here is that many, let's say you have 12 tasks, I train 12 separate transporters with separate demonstrations. However, for the first time this semester, we'll have a lecture on language and behavioral learning. And in that probably last lecture, we'll talk about how you can use extra language input to guide the task. So if the task says put the strawberries in yellow plate, you'll be putting things in the yellow. And then if you tell you put the letters in the holes, you're going to do the other thing, and so on. So then you can use one network to share across all tasks. Does this make sense? Very exciting. That's one paper. We're going to also see many other papers on that lecture. Any other questions? Yes? Yeah. Well, they don't visually show it here, to be honest. Except, let me see, maybe we have some, here there's no rotation, right? That's why you're confused. Okay. Well, here's I have a better slide. Here it is. Okay, so we have the peak and the heat map should light up on the peak location. Here is the orientation, you see? Do you see the orientations here of the patch? You manually orient it. You will orient it. That's it. You'll check your patch and orient it. And this is a parameter-free operation. Just orient your patch of features. And then you will do your, convolutions. Here they are, okay? Of that patch with the peak heat map, okay? And you're going to land with the corresponding correlation maps, as many as the oriented patches. And then you're going to train it so that the corresponding orientation lights up. Do you see? Is that more clear now? Okay, now it's 110, but that's fine. We already covered roughly the transporter network. We'll continue from where we left after the break, after fall break, okay? And hope to see you Friday for our station for the solutions of quiz 1.